For something like 2,000 years, everyone just kind of accepted this idea
Right.
that heavy things fall faster than light things. I mean, Aristotle said it.
He did. And who was going to argue with Aristotle back then? It seemed, well, obvious.
Exactly. It just felt like common sense for centuries.
Eh.
But then came Galilei.
Ah, Galileo.
He looked at things a bit differently. Started to suspect that maybe, just maybe, everything speeds up the same way when it falls, regardless of weight.
Which is a pretty radical thought for the time. But the big problem wasn't just thinking it. It was proving it.
How could you possibly measure that?
Exactly. We're talking the 1600s here.
Mm-hmm.
Free fall is incredibly quick.
Yeah.
Trying to time that accurately with, the clocks they had back then.
Forget about it. It's just a
Yeah.
blur. You can't see the acceleration happening second by second.
It was essentially impossible. You couldn't get the hard data, the numbers needed to challenge, like you said, 2 millennia of accepted wisdom.
So you can't really measure free fall directly. What do? Well, if you're Galileo,
Yeah.
you get clever, you figure out a workaround, a way to effectively slow gravity down.
That's the genius of it.
And that leads us to his famous inclined plane.
The ramp.
Not just any old ramp, though. This was his tool, his gravity diluter, if you will.
That's a good way to put it.
And that's what we're digging into today. How this simple setup, basically a smooth wooden ramp, didn't just poke holes in an ancient theory.
No, it did much more than that.
It completely changed how we approach science. It basically laid the groundwork for, well, modern experimental physics.
Absolutely. It's this huge pivot point. Before Galileo, a lot of science, or natural philosophy as they called it, was based on pure reason, on deduction. Maybe some observation, but not rigorous measurement.
Right. Thought experiments were king.
Galileo flipped that. He showed that the way forward was through careful, repeatable experiments, through measuring things, quantifying them, even with, let's be honest, pretty basic tools compared to today.
Yeah, think about his setup. A smooth, probably grooved wooden ramp, a polished ball, maybe bronze, and for timing, a water clock, basically measuring time by how much water flowed out of a container.
Which required incredible care to get consistent results. Sometimes he even used bells along the ramp, apparently.
Bells. Why bells?
To mark when the ball passed certain points. He could then hear if the time intervals between bells were equal, while noticing the distances covered were getting longer and longer.
Ah, so it helped him understand the timing versus the distance.
Precisely. And what he found was the key. He saw that the distance the ball traveled was proportional to the square of the time it rolled.
Okay, so double the time.
4 times the distance, triple the time, 9 times the distance. And he noticed this pattern in the distances covered in successive equal time intervals.
The 1, 3, 5, 7 pattern.
That's the one, the hallmark of constant acceleration. He basically figured out the math of uniformly accelerated motion.
All by rolling a ball down a ramp.
Yeah.
And timing it with dripping water. It's incredible. He made the unmeasurable measurable.
That's the core brilliance, diluting gravity's effect so he could actually observe and quantify it.
And he showed that this acceleration was constant. It didn't depend on the weight of the ball, just the angle of the ramp, steeper ramp.
Faster acceleration, closer and closer to actual free fall.
Mm.
A vertical ramp would be theoretically full free fall.
Which we now know is about 9.8 meters per second squared. He was uncovering the fundamental rules.
He really was. And the impact. It's hard to overstate. This wasn't just correcting Aristotle on falling objects. It was a fundamental shift in how science itself was done.
From philosophy to physics.
Exactly. From arguing based on logic alone to demanding experimental proof, observable, quantifiable evidence. It demolished Aristotle's physics and, crucially, paved the way for Isaac Newton just a few decades later.
Newton built on Galileo's foundation, right, with his laws of motion and universal gravitation.
Directly. Galileo provided the crucial insights into acceleration and inertia. Newton synthesized it all into his grand theory. Galileo essentially found the kinematic equations without having calculus formally defined yet.
So this simple ramp experiment echoes through centuries of science.
Without a doubt, it's a cornerstone moment.
It really makes you think, doesn't it? What things are happening around us right now that seem just too fast or maybe too slow or too complex for us to really get a handle on?
Like, what are the modern equivalents of free fall that we can't quite measure properly yet?
Exactly. What are the inclined planes of tomorrow? What clever hacks or new tools are we going to need to unlock the next set of secrets about the universe?
That's the ongoing quest, isn't it? Following in Galileo's footsteps.